Okay. All right. Welcome. I think I'm gonna finish the chapter for you here. So this will cover not only Fridays but also Mondays, maybe even Wednesdays class also. Because I think I should just go ahead and close out the chapter. It won't take long. It might be 40 minutes worth of videos, but I appreciated your all's patience today when I kind of got way off script for probably 10 to 15 minutes and explaining kilowatt hours and all that. But those are practical things that a lot of people don't even know where they came from or what's going on. And I think that's very important. And by the way, there might be a test question over, because we cover the kilowatt hour, but it's not till the end of chapter 20. And I don't think we're going to get to the end of chapter 20 between now and our first exam. It'd be beautiful if we could, because you know what? Most of you all are pre-health people, and you need to be in. In fact, I just took my wife to the hospital. She's going through some tests and things. Everything's fine, but he just she should probably kill me for this. But when you start to reach a certain age, things start. Shit breaks. And so you got to get things checked out and need every once in a while you need a tune-up. So the walking around the hospital, though, we're going to the doctor's office's building, everything we passed was quantum mechanics. Everything we passed. In fact, Tyler in our class is a licensed MRI operator, diagnostic operator. I think it's MRI, Tyler. You can correct me later. He intuitively and just by experiment, by using the things, he knows what's going on inside there. The mathematics, doubtful. Hell, there's only 1,000 people who can actually, well, probably more than that, but who can actually do the mathematics behind all that stuff. But we need to get to modern physics, because X-rays, that's where modern physics is. X-rays, MRIs, CAT scans, all that stuff. The only thing that is low tech that saves lives that you guys will use, that almost anybody, to be a responsible citizen should know how to use, is those defibrillators. I've never been through the training, but I can read and I understand the electronics behind it and all that stuff. And I was wondering if I had it here. I don't know if I do or not. Hold on a second. Yes. Uh-oh. Is he doing it? Is he wasting your time again? Maybe. Does he care? No. All right. So anyway, I don't have my little electric stick here, which is also quantum mechanics. So I want to blow through this electricity stuff. One, it's hard, and two, it's boring. It's not boring. I mean, I don't want to say that, but so I want to make it very, very basic. I want to make the questions kind of like the questions on the slide, not much harder than that. And so I appreciated you all allowing me to kind of go off a little bit on a tangent. But anyway, here's where we stop today. Finding the electric potential difference of a point charge. I don't think I've turned on my ladybug yet. And we wrote down the formula. We wrote down the formula for it. There we go. And this is what we came up with. All right, so here is the formula. In other words, if I have a point charge here, and we were talking about that, if I have a point charge sitting here like this, then a distance away from it, there's all of these. Now this is a two-dimensional picture. All of these electric potential field lines coming, potential differences around it, okay? And they're all equal potential. Like, say this might be 12 volts, this one might be 14, this one's, no, that one, I did something wrong there. If this is positive, this can't be 12 and this can't be 14, can it? You're absolutely, it could be negative 14 if all of a sudden we had a huge amount of negative charge. So this would be like 10, 8, volts, things like that, okay? And electric potential, think of it kind of like this. Here's another way to think about it. Electric potential, of course, is voltage, and the electric potential V is equal to K Q over the distance away, okay, over r. All right? And we get that, we figure that because we're going to take this charge, we're finding the difference in its potential. If we take it from r out at infinity, which is r equals infinity, and so kq over infinity is what? 0. So that'll be, we're taking it from, this would be so the initial voltage that we always use is kq over infinity, which is equal to 0. So the final voltage is equal to kq over RA minus kq over infinity, and so that just goes away, and so we just call it V is equal to kq over R. All right? That's it. And one way to think about it is it's kind of like GH. That's like a gravitational potential. So like K over R is your electric potential, and this is like your gravitational potential. In other words, as G kind of stayed the same, K stays the same. As H gets bigger, what happens? As H gets higher, the electric potential energy goes up. Or the gravitational potential energy gets higher. And it's ready to, its potential, it's ready to do more work. It's ready, the higher we get, the faster that sucker's going to be falling, you know. The longer it has to fall and gain speed. Okay, so the GP is going up. All right. So but this one's kind of the opposite. But if we stay on the same H, in other words, and then I'll stop this. But in other words, is there any difference? Say this is a 1.5 meter table, okay, and I've got a book on it right here. Okay, I got this object right here, this 1.5 meter table, and so it's got it off the ground. It's got its gravitational potential energy 1 of mgh. Okay, is there any difference if I just slide it over to here? Keep it at 1.5 meters. Is its mgh still the same? Yes, it is. Same thing. The same thing with, here's my positive charge. Let's say I got a potential here of 10 volts. I got this potential out here of 1 volt. If I move along this line anywhere, along this line, my electric potential energy stays exactly the same. Say this is a positive charge of some sort. This small positive test charge is moving along this electric potential. We move it along this electric potential. It's going to stay the same, EPE10. If I move it along the 1 out here, it's going to stay the same as EPE, this electric potential energy out at 1 volt. Okay? It's going to stay the same. So when they go from here to here, that the electric potential changes. Or if they go from here to here, the electric potential energy changes. Just like if I go ahead and move this guy off and drop him, his electric potential energy changes. Same idea.